First of all, I would like to thank you for the opportunity to present my habilitation lecture today here. Let me start with the reason why it's so important today, in these days, the gunshot detection. In recent years, we are experiencing increase in military conflicts, as well as in threats in public areas, such as lone shooters, or gangs, or even terrorist attacks. And in this situation, it is crucial to recognize the threat quickly, to increase the safety, and to support the law enforcement, like the police or military, to decrease the casualties. Besides visual detection, and acoustic detection plays a key role, for example, in environment where the visibility is limited. In my research, I'm mainly focusing on military applications, solving both hardware and software problems. I'm also aware that this topic is also important in other areas. For example, dangerous situation like glass breaking, human scream, dog barking, and similar. But for example, also to completely another areas like the detection of avalanches in the mountains or poachers in animal reservations. The acoustic detection of impulse events goes back to World War I, where the most simple system has been used to detect the artillery, but nowadays commercial systems mainly focusing on military applications, let's say from Netherlands Avisa to Boomerang, or to French Pillar, or portable version ears. In civil applications, we can spot shot spotter in the streets of Washington, or we can buy surveillance systems from Czech company Jalut. All these systems are capable to detect the firearm, but they are to detect the gunshot itself, but they are not able to recognize the firearm type. And also, by means of localization, they can localize the event, let's say, with the accuracy about 10% of the distance between the sensor and the event itself, or in units of degree in azimuth and elevation. When we speak about the scientific papers, mostly scientific papers deals with the time and frequency features like cepstral coefficient, spectral centroid, zero crossing, or wavelet transform. And when we focus to, let's say, computationally cheaper algorithm, we can experience the energy or transient detectors, filters, or spectrograms. About the detection, the system, the scientific papers usually using time of arrival principle between shockwave and muzzle blast, which limiting the detection only to supersonic ammunition. When we speak about the muzzle blast and shockwave, let's focus a little bit about the theory which lies behind the gunshot detection itself. If a gunshot is taken, if we have subsonic ammunition, there is a muzzle blast pattern which is visible for two calibers on these two figures. And in case of supersonic ammunition, we can also observe a shockwave, which is spreading in a conic shape, depending on the speed of the bullet itself. And these two patterns depend on many phenomena, like the caliber itself, most importantly, but also length of the letter, chemical properties of the propellant, but also on the environment where it has been taken, like the humidity, temperature, but also the environment itself. It has been taken on the countryside, foliage density, or in the city, where we can expect lots of reflections. I also prepare a comparison of the standard ammunition of NATO organization, where you can see the muzzle blast and shockwave. It resembles letter N, that's why it's called also N-wave, with comparison with just ordinary door slam. Again, you can see very similar pattern resembles the N letter. So it's not easy at the first sight to recognize between the impulse event and the gunshot itself. My very first approach was a simple acoustic detector, which has been capable only to detect an impulse event, working on the principle of median filter, which, let's say, frames the signal, calculates some energies and thresholds, and it has been also able, and working on the principle of 4 microphones, and based on time difference of arrival, it has been able to detect the event, impulse event, and to localize it by means of azimuth and elevation, with the accuracy about 4 degree in azimuth and 8 degree in elevation, which is comparable with the commercial system. The system itself has been also able to detect, or it is still able to detect the peaks or abrupt changes in signal, let's say, to signal-to-noise ratio up to 5 decibels. This project has been done with the cooperation with Czech Army, and we have also some functional samples in RIF together with them, since they supposed to use this system in UGV Taros. During my presentation, I will offer you or show you the result presented in journals or proceedings on the bottom of my slide. So I won't be reading it again, but again, all these results can be seen at the bottom. Then we move on, or I move on from the idea of one system, one unit with 4 microphones, and we design another, let's say, idea consisted of standalone units and a distance server, where each and every unit containing 1 microphone. And this time we focus to be able to distinguish between the gunshot itself and the event which resemble the gunshot. This system has been able to delocalize the event itself if at least 3 units detect the threat itself, and based on time difference of arrival, it has been able to calculate the latitude and longitude of the detected unit. When I say, or when I said that we were able also to somehow recognize the gunshot and the false alarms, we use, or I use, 2-stage detection, the modified median filter, which has been introduced to you a couple of slides before, and the second stage using a couple of different methods, from the frequency domain methods to time domain methods to combination of both, to cepstral coefficients. It has been revealed that the frequency methods more or less identify the environment itself and the reflections from that environment, while the wavelet itself, depending on the mother wavelet, are focusing only on some specific shape of the event itself, of the gunshot. So it wasn't so good in recognizing between different ammunition type. While the frequency cepstral coefficient shows relatively promising results to the future. We performed some experiments under specific condition. It was on the shooting ranges, semi-open and open. We have only 3 calibers, but we were able to distinguish a gunshot at 100%, but we still have relatively very high false positive occurrences. which which I know that we need to decrease it. And we were, I was also able somehow to recognize between the different calibers with, let's say, promising accuracy. Then I move on to design, or let's say to optimize hardware, but also the software of the system itself. We designed the prototype, which has been powered by the batteries, used GPS synchronization, used LoRa for communication, and the principle was similar, to have some stationary units and distance server where the units perform the detection and identification algorithms, and the server itself performs the localization. We use the same two-stage detection, the median filter, which is capable to detect the abrupt changes, the peaks, and the Mel frequency cepstral coefficient. The system itself works, the localization of the system itself works on a different time of arrival reverse principle. What does it mean? It means that we calculated the spreading of waves from the units which detects the threat, and the intersection of all units was the event itself. The system is capable of 3D localization. We use nonlinear least square optimization Lavenberg-Marquardt method with the accuracy about less than 10% of the distance. Here on the graph, it's some experiments where for the distance about 100 meters we have accuracy error about 8 meters in localization. We tested this on diverse military shooting ranges, also to detect or to recognize the ammunition type. And that time we not only focused to distinguish between different, between the gunshot and, as I call it, false alarms, but also to different ammunition. We had 8 different classes. Calibers with diverse ammunitions, and this table gives us some overview in classification accuracy. For classification, we use support vector machine, or I use support vector machine and neural network, but I mainly focus on support vector machine principle since I have some experience from my previous work, so the neural networks wasn't the main classifiers in that time for that part of the work. When we speak about the training and testing set, I use about 2/3 for training and the rest for testing, and the result can be seen here also in confusion metrics, where again the relatively high error of false alarms was still there, like the false positive ratio. So that's why I focus more to the classification part, to be able to better recognize not only the individual ammunition, but also the false alarms itself. I still stick to frequency time domain combination as a feature extractors. So I use the cepstral coefficients, and also try a different length of the frames, median filter framing the signal. We will be speaking about different length of frames maybe later when I will be answering the questions of the reviewers. We also try different number of filters, features for classification, and most importantly, different kind of cepstral coefficients, from Mel frequency to linear frequency, inverse Mel frequency, to most importantly, gamma tone frequency cepstral coefficients. And for classification, we still use support vector machine and neural network. In our experiments, we created our own database in Parquet format. It contains only samples recorded by us from diverse gunshots type, let's say, or ammunition type, and also calibers, most commonly used in the European and Asian continent. And we also recorded, again, only over false alarms resembling by its shape the gunshot pattern itself. So we focus on various slams, hand claps, bubble wraps, pooping, etc., etc. I choose an example just to compare, let's say, the accuracy of different feature extractors. We have 4 classes and false alarms, and on confusion matrices here you can see that the gamma tone cepstral coefficient outperforms the others while reducing the false positive occurrences to, let's say, under 10% under specific conditions. Here there is some overview of different feature extractors, different frames of length for both classifiers, and some measures how good we can recognize the gunshot type of the ammunition itself under some specific condition on diverse military shooting ranges, open, semi-open. I choose accuracy, recall, and Matthews correlation coefficient. Why Matthews correlation coefficient? Because we were unable to record, let's say, similar number of samples of different ammunitions. From 9mm or 5.56 NATO, we have much more samples than, for example, from Magnum caliber. And Matthews correlation coefficient respect the imbalance in the size of the samples. Matthews correlation coefficient is defined from -1 to 1, where the -1 is completely wrong, 0 is random, and 1 is almost perfect score. And again, for the neural network and gamma tone cepstral coefficients, in our experiments we were achieving almost perfect score. But again, only some under specific condition in military applications. Then I focus in improving the accuracy of the system itself. I leave the idea to have individual units with one microphone, and we design 2 microphone units, which has been optimized for urban areas because it's powered over the Ethernet. It can be also mounted to, for example, military vehicle, and it only performs basic processing and calculation of angle of arrival, while the identification and localization is calculated on the server. It used the gamma tone cepstral coefficients. The angle of arrival itself is computed by determining the time delay between the 2 MEMS microphones. So if you have at least 2 units mounted, for example, on some object, it can define where the threat is. We also design our own algorithm to, let's say, increase the accuracy of the time delay between 2 microphones. We used phase-based spectral methods, which principle is here. So we are windowing the signal itself. We are using asymmetrical window, which resemble the shape of the gunshot itself, the end pattern. Then we calculating FFT, choosing the important frequencies through the frequency band, and looking for the angles in the phase spectra. Then we wait the result, and we tested this algorithm in anechoic chamber and also military shooting ranges, and compares the result with, let's say, most commonly used method like correlation functions or correlation function with phase transform. this dependency shows how our algorithm perform under relatively high noise. So we also added artificially additive noise peak signal to noise ratio and measure it for let's say different angles and compared the mean error with the other methods where our algorithm performs let's say twice as good under high noise than the others. The last graph shows so-called visualization of the method itself, where each and individual point stands for the frequency, its size, for the weight itself, and the resulting delay. It's like statistically processed the result of the most important frequencies. Now let me conclude my habilitation lecture. I'm a lead developer of the hardware, algorithm design, implementation, and testing of an acoustic surveillance system, which is capable of identification, detection, identification, localization of the gunshot. Its result has been published continuously during the research in Q1 or D1 articles. And a key aspect of my work is to use a real-life scenarios data, which has been measured only by us, and through the collaboration with the Czech Army. I also formed a team consisting of department researchers, master and bachelor degree students, as well as an international student participating in semester or team projects. And recently, I'm also supervisor of 2 Ph.D. students. In future, I want to aim to increase the training size and diversity, and we want to improve the system to be, let's say, able to self-learning mechanisms powered by AI to adapt to new sound events and scenarios autonomously. And also right now we are also trying to be able to detect also the artillery, so we are starting cooperation on another topic. Before I stop my presentation, I just want to show you one of my side quests during the research. We also let's say observe that in some kind of microcontrollers which use analog to digital converters based on successive approximation principle and containing no buffer, that if you connect the circuit with non-negligible output resistance, the measurement itself can be affected by the input currents, and these input currents are also different for the different inputs of the analog to digital converter. We propose some solutions, some models, and present it in a D1 journal. Should I read also some? No. Okay, so that's it of my presentation. Thank you for your attention.
Thank you for interesting. Yeah. Thank you for introducing the topic, which is very up to date today due to the international circumstances, and thank you for keeping the limit. Now I open the floor for questions for the audience. Professor Svoboda, I will ask my assistant, Magistra Hakenová. So, Professor Svoboda.
Okay. So, actually, my question is how small it can be. I mean, the sensor itself. I suppose that from many pragmatical reasons, you want to make it as small as possible. And I suppose there is a theoretical limit depending on the frequency of the wave and all the stuff. So did you study this?
You mean the whole system itself?
Yeah, well, the measurement sensor, actually, yeah.
Yeah, usually if we want to use it depends on the IDE itself. If we want to have the computational power inside the sensor, to be able to also identify, or if we just...
well, for the moment, ignore the computational power, the needs, where to place the computers, and so just the microphones, actually.
Smallest units we are using is this one, which is about 20 centimeters in the distance between two microphones.
Yes, and what's the limit of this kind of this device?
It depends on the precision. If we are speaking about two microphone units, it depends how precise we want to calculate the time difference of arrival when we are comparing the distance and the sampling speed.
Yeah, obviously. So, second question on it. So, if you know the requirements, think about that. You know the requirements, like someone from the army knows what the army wants and comes to you. So are you able to compute the minimal possible sensor, a minimal possible shape, minimal possible configuration of this sensor if you ignore the obvious noise problems and so on?
I didn't think about this in this way, but my estimation would be, let's say, about units of centimeters, let's say up to 10 centimeters to have a sufficient distance between the microphones.
Okay, and if I may, the last question.
Yes.
So you spent quite a lot also on the say software part of your approach. So my question is, how much is the software part independent of the hardware one? Did you apply your software methods also on some other sensors?
Yes, we use different types of microprocessors, let's say, and also different types of sensors, like the electret microphone, MEMS microphones, and I think in these days with MEMS microphones with digital output, I think it can be applied on different hardware, let's say, even on small embedded systems.
Okay, thank you.
Thank you. Professor Železný.
I think you said nothing about the performance of existing devices of this kind. So are you really the first person to...
When we start with this research, I think, and I would say that we were first who were trying to distinguish between different ammunition type. Maybe the Israelis have it, but they don't publish it at all. And all the systems back in these times were only able to recognize the gunshot itself, but not the, let's say, ammunition type, maybe caliber, but not the ammunition type. And the thing is that the caliber, you can have one firearm, one caliber, but different diverse ammunition types.
Okay, so your claim is that in the public domain there are no previous...
Not in these times when we started.
Oh, okay, fair.
Thank you. Professor Matás.
Okay, I have two questions. One is about the modified median filter. Maybe I missed it. What is the modification?
Yeah, it's here. It's not, let's say, a typical median filter. We are framing the signals. We are still looking on the middle window or top, as I let's say, name it. And we have an odd number of the different tabs, and we are calculating the means through the tabs, not through the individual samples, but through the tabs itself, and subtract the background from the other tabs from the let's say actual one to suppress the background itself.
Okay, and I think one thing is about methodology. Just on page 10, for instance, when you show the results, I think, in at least the way I use this terminology, what you call false alarm is not a false alarm. It's a non-gunshot observation, and it becomes a false alarm if it is classified.
If it's detected, yes, yeah. You're right. Yeah.
So the original, by original predicted in the top left corner of the bottom table, you mean what it is in reality, the truth. So it's not a false alarm; it's a non-gunshot sound.
That's correct.
And then it's better to put these things in rates. Yeah, like so. Probably you have. It's like from this, it's very difficult to see. So you have 50 correct decisions, 13 incorrect. So 13 over 63 is your not 13. Yes, 13 over 63 is your false alarm rate, and it means that something like every sixth
yes.
sound from the set you tested. I don't know, door slam, hand clap. Of course, if you have it.
Yeah, that's correct. That's why we
so
focus.
You shouldn't use the word false alarm. Depends on the decision, not on the signal itself.
Okay. Yeah, thank you for this comment. You're right.
Thank you. And Professor Železný, once again. No?
Just a follow-up on my previous question. Are you aware of the paper called Gun Identification from Gunshot Audios that was published in Nature Scientific Reports in 2022?
We started like 3 years before this, in 2019.
Well, okay, they claim to achieve 94% of accuracy, but that may not be comparable because you may have multiple
And
classes
it's
so
based
on
the acoustic detection?
from gunshot audios.
Okay.
So I would still be probably a little bit happier if there was a little bit of state-of-the-art review.
Yeah.
The lecture, but anyway, that's all for me.
Yeah, thank you for the comment. Professor Straka.
Thank you for the nice lecture. I have a question regarding the localization. So you mentioned that you use AOA and TDOA measurements. So for the localization itself, you use least squares?
You mean the resulting?
Yeah.
Yes.
And for that, do you use some information about the uncertainty or quality of the measurements? Because in this case,
you mean the uncertainty, for example, the detecting of the peak? I mean the time when we detect the peak.
Yeah.
Yes, we done it. I didn't put it to my lecture, but we done it in this part. Okay, it's only about the elevation and the azimuth, but it depends on the sampling, and if you are able to detect the shape, or how to say it, the edge of the system correctly, and the uncertainty is included in this accuracy actually.
Okay.
So it depends on the sampling frequency and also the processing circuits.
Okay, and the last follow-up question: how did you identify those numbers, those accuracies for different signals, for TDOA and AOA signals?
Maybe I don't get correctly your questions. We done it from the sampling rate, let's say. There is some uncertainty between two samples. So if you detect T1 with the distance between two samples, that's the uncertainty of the given sample of the edge itself, which will produce some uncertainty in the azimuth, for example.
Okay, thank you.
Professor Svoboda.
So out of curiosity, so what is the range of this device, operation range, in a normal day and in a quiet night?
I think that I can't answer on this question like in meters. I can say that if there is some, let's say, measurable abrupt in the signal, some peak, let's say up to 5 decibels signal to noise ratio, and we are able to detect this peak, we can do.
Yeah, I saw the 5 decibels there, so I just wanted to translate in my units that I know. So
it really depends on the environment. Yeah,
but I can imagine. Just
again, if we will be speaking about I don't know, semi-open shooting ranges where there are some walls and some obstacles, it will be less than 100 meters, I would say.
And just because
with some background noise.
And how does the approach change when you put the sensor on a moving on a moving platform, say on a different vehicle?
That's something we want to deal with.
Okay.
Yeah.
Děkuji. A další dotaz, pan profesor Havran.
Thank you for your lecture. Work. Thank you for your lecture. I would like to ask you for the change of accuracy because of these conditions. In particular, if you are indoors or outdoors. So this accuracy is the best outdoors.
Outdoors, yes.
So, and is there also, let's say, dependence on the temperature, humidity, pressure, and these things, or is it in your sensors as well that you can compensate for that?
Yes, it's not visible here, but we are working also with the temperature and the humidity of the environment itself. But to be honest, the influence of these parameters is not so high. The most problematic things are reflections. So if there will be reflections, I shouldn't tell you, but there is a problem. We are not able to detect if we will have lots of reflections which will be mixed. But if we will have the sensors which will have the direct visibility, at least one of them, I think that we should process it somehow. But again, this system has not been tested, let's say, in some closest spaces, only on semi-open, usually without the roof. But there are still reflections from the ground and from the obstacles.
And did you work with the simulation of the acoustic, let's say, sound?
Yes.
For example, that the model is really like in reality is fitting to your.
When we are speaking about the localization, yes, we perform some simulations with. I have results, but again, I didn't put it to my presentation since I wanted to fit to my time. But we perform the test with the ideal number of sensors which will be detecting the event itself and also the distance between them. And we also simulated the delays caused by the environment, caused by the reflections or, for example, foliage density. And yes, I have results. So usually it's about 10%, as I showed you before, about 10% of the distance, the accuracy.
Thank you.
Thank you. And Professor Kittler.
Thank you for your presentation. Deep neural networks are now standard for solving any detection classification application. What is the main reason why you are not using this technology?
Yeah, thank you for your question. I'm not an expert in neural networks. We use convolution neural networks, and we use it since we know that it performs the best. But there are still lots of work about designing or optimizing the neural network itself. As I said before, I have experience with support vector machine classifier, so that's why I primarily use this one with different kernels. And I just wanted to compare the result of something which I know about a little bit, let's say, with something I need to learn. So that's why.
Thank you.
Thank you. So if there are no any other questions, thank you again for the lecture.